welcome to episode 5 of Explaining Physics Concepts. In this video, we're looking at electric fields, and all of these topics will be covered. So let's just begin. We're going to take the same trajectory as we did for the gravitational fields. There was law of gravitation. Here we're going to take a look at Coloumb Law. So what is Coloumb Law? It's the exact same definition as that of gravitational field. You just have to change a few words. The force of attraction between 2 point charges. The force of attraction between 2 point charges. This word point is very important. The force of attraction between 2 point charges is directly proportional to the product of their charges and inversely proportional to the square of their separation. So if you remember the definition for law of gravitation, the force of attraction between 2 point masses is directly proportional to the product of the masses and inversely proportional to the square of separation. Now if you put all of this in an equation, you'll see that the force is directly proportional to the product of the charges Q1 and Q2 and inversely proportional to the square of their separation. So this is literally the how you put it in this way. And if I were to convert it into an equation, obviously when I have to remove this, I have to put a constant, and that constant in this case is KQQ over R square, and K equals 1 over 4 pi E naught. You will be given this, but it's best if you just know this. And this 4 pi E naught is the permittivity of free space. Just an added note, E naught is permittivity of free space, and its value is given at the beginning of the exam as well. Now whenever you get these weird or difficult chapters like these, what I suggest is that you break it down, right? So that, like I have broken it down here, it's Coloumb law, then you break it down to electric field strength, electric potential, and graphs. So that way your brain, it creates sections itself. Let's say we're going to talk about electric field strength here, and right here we're going to talk about how do you make it straight. Okay, never mind. We'll just use this. And here we're going to talk about electric potential. So very similar to gravitational field strength and gravitational potential, but again, there are the differences as well. So first of all, first point, electric field strength. Electric field strength, it is a vector quantity. That means plus minus, they play a big role. It's a vector quantity. And for point charges, do you remember the formula for gravitational field strength? That was m over r square, gm over r square, right? So for this, it will be E equals q over 4 pi E naught r square. And this is for point charges. Now what is a point charge? For something to be a point charge, it should be spherical. It should be a spherical conductor, right? Now electric field strength is a vector quantity. Then we have the formula. But what if you have electric fields? Electric field is essentially the force acting per unit charge. Force acting force acting per unit charge, and that is again E equals F over Q. So again it's the similar E and E symbol, both of them are similar. So E equals F over Q equals Q over this. If you are given a point charge, if the question states that it's a point charge, you will be using this formula. If you're looking at electric field, we're going to be taking a look at F over Q depending on what information is given to us, right? It's very similar to saying G equals F over M. You do remember F equals MA, right? So G equals is very similar to that. Now, what if you have uniform electric fields? Now here is the catch: uniform electric fields. Now for uniform electric field, that is E change in potential over distance. So this is change in potential and this is distance. Now a lot of people, they confuse this. There is a difference between electric field strength, that is only the formula for electric field strength, E equals Q over 4 pi E naught R square. That is only and only for point charges. Then you have electric fields, E equals F over Q, and then you have if there are uniform, if the word uniform is given to you, uniform, the moment you see this word, that is when you have to use this. Now let me make a drawing for you to understand it better. Let's say you have this, and then you have this, and plus, this is negative side. Now they are uniform, that means they are separated by an equal distance. So this is what makes it always goes from positive to negative. So this is what you call uniform electric fields, and so this is the distance. This is the distance, this is the change in potential. So if these things are given to you, that is when you use this formula. Otherwise you can use E equals F over Q, and if you're given a point charge, that is when you use E equals Q over 4 pi E naught R squared, this one. Now another thing, I will draw the electric field strengths of positive charge and negative charge. So if you have, let's say, let me use this, okay. So if you have a positive charge, and then I'll make a negative charge here. So if you have a positive charge, these are all the electric field strengths. And you have this, then you have this, then you have this, and then you have this. So all of the arrows are away from the positive sign, and then when you have negative, let me just draw these lines first. All of them are very straight, very uniform, something I mentioned in gravitational field chapter. All of these arrows are towards this. So keep this drawing in mind because it's extremely important for the upcoming graphs that will be coming. So this is one part of it. Now let's move on towards electric potential. So what do we mean by electric potential? So electric potential, again very similar to what we did in gravitational field. Electric potential is at a point exact similar to what we did in, let me make it white. Electric potential at a point is the work done per unit positive charge in bringing a small test charge from infinity to a point. So if you remember the definition from gravitational potential, that was gravitational potential at a point is the work done per unit mass in bringing a small test mass. So we're just changing mass from charge. And what is electric potential energy? Now For the electric potential, again very similar formula. V equals Q over 4 pi E naught R. Do you remember G equals M over 4 GM over R? Yes, that was what we had for this. And when you have electric potential energy, all you have to do is just add another charge, Q over 4 pi E naught R. Again, if you remember gravitational gravitational field chapter, that was V equals Gm over R, and then for the potential energy it was Gmm over R. So I just want you to just, whenever if you have difficulty, you just remember this, and then you can bring, all you have to change is change this mass with charge and change this constant to 4 pi E naught R. That was electric potential and electric potential energy. Now there is something I would like to do. And that is now for the gravitational, we had a negative sign here. You can do that here because it's both repulsive and attractive in nature, so you do not need to put any sign here. Now generally, if you were to look at the electric field, if you have positive, 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 and here you have negative, 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 and generally if it's not uniform, so if you have, let's say, a charge that is entering, the charge, it goes like this, and it just, so what we call this, so this is a positive charge, so obviously it will be leaning more towards the negative side, right, because they will be attracted to each other. So when you look at this is what you call a projectile motion. So generally you say that whenever a charge, positive or negative, it enters an electric field, so that is that is called a projectile motion. It's not circular. Why? Because the angle here, the angle is 90, here the angle is 90, but here the angle is not 90 anymore. So it's a projectile motion, and it's not circular, it's only a projectile. So it goes like this, it does not go like this, it goes like this. This was one part of it, and now we're going to move on towards the graphs, which confuses a lot of students, but I'm going to make it easy as I can. So let's begin. So when you're looking at graphs, there are 4 graphs that we have to deal with, and we're going to take it step by step. First is for the unlike charges. So the moment you think of unlike charges, you come up with this diagram, the one that I just drew up, this one, right? So unlike charges, that means, and I have a positive, negative, and then this. Let me just draw these, and it's always away like this. And then for the negative, it is towards. Okay. Now for the what the graph that we will be drawing is the first graph that we will be drawing is this E. If this is electric field strength, I don't know if this confuses any people, but if it does confuse someone to differentiate between E and V, this is for electric field strength. So it has 3, electric field strength, and this is only 2, so electric potential. So you can think it that way as well. So this graph is for electric field strength against x, which is distance. Now the electric field strength is a vector quantity, so, and it is for unlike charges. So do you see how this electric field strength is going in this direction, and this electric field strength is also going in this direction? So do you see they are going in the same direction? They're going in the same direction, so they are reinforcing each other, right? That is how you can look at it. They are reinforcing each other. So the graph will be like this. It will never touch it will never touch this baseline, because the electric field strength can never be 0, can never be 0 for unlike charges. Why will it be 0? Because it can be 0 because both of these are in the same direction, so they're just reinforcing each other. So it's like saying this is in +1, this is also +1, so +1 +1 is going to give you +2. That is how you can look at it another way. Now, the other graph that we're going to take a look at is, you know it is going to be electric potential against distance. And for this graph, how will you think about it? Now for the electric potential, let's say the electric potential of this part is plus VA, let's have it as A, and for this we're always going to add the potentials, and for this it is minus VB, let's have minus VB. Now what do you get? Both of them are unlike charges, both of them have equal potential, so VA minus VB, that will give you 0. So at one point it won't be 0, it will be VA equals VB. So this is something that confuses a lot of people, that at one point the potential it gets 0. Yes, at that point when we say the potential is 0, we say that the potential of the charges is equal. So the graph will look like this. At this point, this is the exact point where this happens. We don't say that it becomes 0, we say that the potential of the charges, it becomes equal to each other. So this is the point where you can put them equal to each other. Now here is another important thing that I would like you to hear, very important actually, that is, what's the gradient of this? You do it, y over x, right? So that is v over x. And since it's in the negative direction, so it's minus v over x. Now, hear something out. The gradient of this will give me the electric field strength. Why? Because if you go up, if you go here, do you see this? E equals V over D. That is exactly what is happening here. The gradient V over X is giving me the electric field strength, but the gradient of V over X, and this is what you call potential gradient. You call this potential gradient. Now, the gradient of V over X gives the electric field strength with an opposite charge. Do you see this negative sign? It gives me the electric field strength with an opposite charge. That means if I have a positive gradient, okay, hear me out. Let me explain this. When you have E equal minus V over X, let's say the gradient V over X, right, the V over X is, let's say, positive, right? So positive 2, that would give me negative electric field strength. But if I have, let's say, negative gradient minus 2, that would give me positive electric field strength. So the point here is that the gradient of V over this gradient V over X, it gives the electric field strength with an opposite charge. So that means if the gradient is positive, the electric field strength is negative. If the gradient is negative, the electric field strength is positive. So if I were to sum it up, all you have to say, if gradient, which is V over X, if it's negative, then electric field strength is positive, and if gradient is positive, then electric field strength is negative. And this is the entire science behind this. Now, we're going to move on towards the next set of our graphs, and that is like charges, which means I can take a positive, and here, it's going away, and then I'm going to take another positive because like charges, and then you have here, it's going to move away. I drew this here accidentally, so let me just erase it. So it's going away. Now, do you see? It's going in this direction, it's coming in this direction, they cancel each out. That means for the graph of electric field strength against distance, the graph will look very similar to like this. Now, why is it not touching this like the V? Why? Because the reason why it's not touching is because whenever you have a charge inside the electric field strength, there is no electric field strength. There's like infinity, right? So that is when you have this graph E over X. It becomes 0 here. Why does it become 0 here? The reason why it becomes 0 here, that is because of the like charges. They're in the opposite direction, right? But if you look at it here, the field strength is 0. That is why we're not going to touch it. We're just going to start from a certain point, right? But what happens when you have to take a look at the graph for V against X? Now again, you have both of them are positive, they're going to reinforce each other. So we're going to start it like this, not like this. It's not going to touch because it's reinforcing. So they're kind of similar. You just have to understand that whatever happened to electric field strength graph, and unlike charges, is happening to the potential graph. So that is how you have to make this graph. So when we come to like charges, they are reinforcing each other in potential, but since electric field strength is a vector quantity, so I have to take the direction as well. So I have to take into consideration the direction as well. That is why I'm stressing upon the direction, that it is in this direction, it is in this direction, they're in opposite directions. You get 0 at this point. But here, for this graph, the directions were in the same direction. Here they're reinforcing each other, so it never becomes 0. And that is what we did it for the electric field. The next part of this is capacitance, but we're going to do that in next video. And this chapter, it may seem confusing right now, may seem all over the place, but I'm going to upload a lot of weird questions that include these graphs, so stay tuned for them, and I'll be putting them all in a playlist, so make sure you check that out so you can understand it better.